Welcome, everyone. Today we're going to demystify some of the most commonly misunderstood concepts in statistics: p-values, confidence intervals, and the reasoning traps that trip up even experienced researchers. Here's what we'll cover: what p-values actually mean, and the three things they cannot tell you, type 1 and type 2 errors, the two ways every statistical test can go wrong, confidence intervals and why they're often more useful than a single p-value, real-world examples that show how statistics can mislead when taken at face value. The goal isn't to turn you into statisticians. It's to give you the critical thinking tools to read studies, evaluate claims, and ask the right questions. Let's get started. P-value is the most misused number in science. Most people treat it like a binary verdict. Below 0.05, the drug works. Above 0.05, it doesn't. That is not what it means. Here's the precise definition. If there were truly no effect, the probability of seeing results at least as extreme as ours, purely by chance, is X%. It's a probability about your data, not about your hypothesis. It does not tell you whether the treatment works. It does tell you how surprising your data would be in a world where it didn't. Three critical things it cannot tell you: the magnitude of the effect. A P of 0.001 on a 0.2 liter per day milk yield increase is not clinically meaningful. Whether the null is true, a P of 0.06 might reflect a real effect in an underpowered study. And whether the result is reproducible, one significant p-value is one data point, not a settled fact. Two ways to be wrong in opposite directions. Type 1 is the false positive. Your test says effect exists, but it doesn't. Happens about 5% of the time when the null is true. That's what alpha of 0.05 accepts as the price of using statistics. Type 2 is the false negative, and this is where most mischief happens in small veterinary studies. The treatment works, but your study was too small to reliably detect it. You conclude no significant difference, and people read that as the drug doesn't work. Wrong. It may mean the study was underpowered. If a study has 30% power, common in small veterinary trials, it will produce a non-significant result 70% of the time, even when the treatment genuinely works. That's not science. That's noise with a p-value attached. Winner's curse is important. Small, underpowered studies that happen to cross the significance threshold tend to dramatically overestimate effect size. A large random fluctuation was necessary to push them over the threshold, and large fluctuations overestimate truth. So, when you see a dramatic first finding from a small study, be appropriately skeptical. Replication almost always shows a smaller effect. Think of the p-value as a light switch, on or off, significant or not, nothing else. Think of the confidence interval as a speedometer. It tells you how fast, which direction, and how precisely you've measured it. Use both, but the confidence interval is the richer instrument. The null value is your reference. For differences, null equals 0. For ratios, like odds ratios and risk ratios, null equals 1. If the confidence interval doesn't touch the null, the result is statistically significant at the level corresponding to your CI. A 95% CI corresponds to alpha of 0.05. The bottom example on the slide is important. A narrow CI running from 0.92 to 1.08 is not significant, but it is informative. It tells you if a real effect exists, it's tiny. You've ruled out anything clinically meaningful. That's a real null finding. Contrast that with a wide confidence interval spanning from 0.5 to 3.8. That means you don't know whether the effect is large, small, beneficial, or harmful. The study was underpowered, and the conclusion is we don't know, not there's no effect. With a large enough sample size, almost anything becomes statistically significant. 2,000 dairy cows, a feed additive that increases yield by 0.2 liters per day, P equals 0.001. Real effect almost certainly, but is 0.2 liters per day per cow worth changing your feeding program? That depends on additive cost, management burden, and whether 0.2 liters moves the dial on farm profitability. Statistics cannot answer that. Clinical and economic judgment must. Place every finding in one of the four quadrants. Top right, significant and important. Act. Top left, significant but trivial. Don't let a statistically significant finding drive a clinically unjustified change. Bottom right is the most commonly misread, not significant, but potentially important. This is the underpowered study that couldn't detect a real effect. The right response is seek better evidence, not conclude it doesn't work. Bottom left, not significant, not important. File it and move on. 7 takeaways, but they reduce to 3 habits. Know what P means and what it doesn't. Know what the confidence interval adds, and always ask whether the effect size matters clinically, not just statistically. The mental image of a p-value of a light switch is helpful. The p-value gives you a binary signal, on or off. The confidence interval, represented by a thermometer, gives you a continuous measurement in context, direction, magnitude, precision. Both belong in every results section, but if you had to choose one to make a clinical decision from, the confidence interval carries far more information. One final point on winner's curse. When the first study of a new intervention shows an odds ratio of 8.5 with P equals 0.02 in 40 animals, be skeptical. The next well-powered study in 400 animals will almost certainly show a smaller effect. That's not because the treatment stopped working. It's because small studies that happen to reach significance are statistically biased toward overestimation. Read the literature with that bias in mind. This scenario applies everything from Talk A in one realistic case. Pause the video and see if you can work through the questions. Then we'll work through them together. Question 1 answer, not significant. Absolutely does not mean the drug doesn't work. Look at trial 1's confidence interval, -26% to 2%. This is telling us the true risk difference is consistent with anything from a 26% harm to a 2% benefit. The study was far too small to distinguish between a highly effective drug and an ineffective one. We don't know is the honest conclusion, not no effect. The wide confidence interval is the honest representation of that uncertainty. The p-value alone, 0.09, gives you none of this information. Second question answer. ARR equals 24% minus 20% equals 4%. NNT equals 1 divided by 0.04 equals 25 calves. The result is statistically significant. Whether it's clinically meaningful depends on cost versus benefit. If metaphylaxis costs $12 per calf and each BRD case costs $200 in treatment and weight loss, you'd spend $300 to prevent one case worth $200. Economically negative. Statistical significance has confirmed the is real, economic analysis determines whether it's worth acting on. Question 3 answer. Trial 2 is far more reliable, 800 calves per group versus 38. Trial 1 was so underpowered that its non-significant result carries almost no information. Trial 2 had adequate power and produced a precise estimate, a narrow CI confirming a real but modest effect. More animals means the estimate is closer to the truth. If forced to make a clinical decision on one result, always prefer the adequately powered study. Question 4 answer. The colleague's conclusion is incomplete in 2 ways. First, a p of less than 0.05 confirms the effect is real. It says nothing about the size. An ARR of 4% and NNT of 25 may or may not justify metaphylaxis depending on cost and stewardship context. Second, it ignores the clinical significance question entirely. A statistically significant trivial effect does not justify a management change, especially one involving antimicrobial use. Question 5 answer. The pooled CI will be narrower than either individual study's CI because combining data increases the total effective sample size and reduces uncertainty. It will be centered somewhere between the 2 point estimates, weighted more heavily toward trial 2 because it's far larger and more precise. The pooled CI will almost certainly exclude 0, confirming that the drug has a real, if modest, benefit. The pooled estimate will likely confirm an ARR in the range of 3 to 5%, consistent with a real but modest treatment effect.